So first of all, I want to say that this is a rather large project. Daniel Lee's here. This is sort of the list of the team in order that we joined. Andrew hired me and Matt to solve some statistical fitting. And 5 years later, we now have a team of like 20 developers and a rather big project. So unlike everything else I've done in my life, I've been working on the same thing for like 5 years in a row now. So what is STAN? It's an imperative probabilistic programming language. My background's in computer science and natural language processing and programming languages, even though I'm in the stats department. And it's an imperative programming language like C or like Java, well, parts of Java like R, parts of R. Unlike Bugs or Church or Figaro, which are other contrasts you may have heard of that are different types. So a STAN program, and I'll show you some examples later, declares data and constrained parameters and defines a log density. And then we provide automatic inference on top of that. We do MCMC, Markov chain Monte Carlo for full Bayes. We can do black box variational inference, and we can do maximum likelihood and penalized maximum likelihood. Why do we want to use STAN? These models are very hard to fit, right? If you try to build things yourself to try to fit these models, you will find yourself spending your whole career recreating the algorithms we created underneath. We have very efficient ways of handling constrained parameters like correlation matrices or simplices. We can do very general multi-level linear modeling. We have a lot of multivariate support in terms of linear algebra and underlying operations. We have differential equation solvers built in. We actually do a lot of chemistry rate equation stuff, mainly in pharmacology. And we have Gaussian processes, for instance. And the language is very general. It runs on all the standard platforms. We've recently pulled out the underlying C++ library. So there's a C++ library that computes all of our math library with derivatives of first, second, and third order that you can use, and that's all exposable through our various interface languages. So we can run in all these different languages. The command stan, rstan, and pystan are native interfaces, and everything else wraps from a higher level. We also have some high-level interfaces now on top of STAN, right? Instead of just coding models up directly yourself, we have ways that you can write these up like R, regression expressions. We have graphical interfaces for exploring posteriors of Bayesian inferences and doing cross-validation. And you can pull this all out as IPython notebooks and run them pretty much anywhere other than Windows. Who's using STAN now? We've got over 1,600 people now registered on our users group. There are on the order of 10 or 20,000 manual downloads. We don't actually have a good way through GitHub to track real downloads, I don't think. There's been a couple hundred published papers that people have written across. These are just areas where people have actually published peer-reviewed papers using STAN, and this list is about a year old. So we're getting use across, what's really exciting us is we get to do science, right? The fun part of this project for me is I get to go hang out with all these scientists and do science through the statistical side. We have extensive documentation for this if you're getting started. We have lots of tutorials. We have a very detailed manual. We have installation and getting started guides for all of our different interfaces. There have been 4 different popular stats books where all the examples have been translated to STAN, and books are coming out now that are actually about STAN or include at least chapters about STAN, a couple of which we're writing ourselves at this point. And just to give you a feeling of what an actual STAN program looks like, I'm just giving you very simple ones. People write like long STAN programs to do complicated things. This is just a model for logistic regression. So you declare what the data is, what the shape of your data and the types of your data is. You declare what your parameters are, and then you declare your density function, basically a log density function there implicitly. So there's a Cauchy prior on the regression coefficient. And then we have a logit scaled Bernoulli that you can use directly with linear algebra operations. So you can write these models down for statistics in pretty much exactly the way they look in well-written papers, or especially in machine learning papers. Right, if you want to do like time series regressions, those are very simple. You just have a slightly different likelihood function. There's no priors here. STAN doesn't require you to use priors. We can also do maximum likelihood fitting. This is something that we're very excited about. If you're doing multi-level modeling, you're trying to do like population modeling and then infer things about individuals, like in the problem you were talking about markets. You might want to model the population so you know what to do for new users. Often you want to do that with covariance type effects and on the random effects in your model. So this is an example of how we can do multivariates with Cholesky factors very efficiently. And here's a short example just to look at, which is the last slide I've got, which does Gaussian processes. So this is a squared exponential covariance function for a Gaussian process. So you just basically, again, just code up the data, the parameters. You define the covariance matrix there, and then you write the density down that you care about. So I will stop there. I think I actually did that much faster than I thought I would. So I'll leave you with the picture of the namesake. It's not an acronym. It's named after Stanislaw Ulam. So despite the T-shirt, don't print it in all caps.
Do you have some modelization framework behind of this?
Some what framework?
Model selection.
Model selection framework. Well, we do leave one out. We generally like to select models based on predictive performance, so we do leave one out, cross-validation or held out cross-validation. But what we're primarily care about is making sure our models are calibrated, making sure that when we make a prediction that 50% of the time, right, this is going to happen, that in fact 50% of the time that really does happen. Right, so rather than a lot of the machine learning models, which are doing maximum likelihood and aren't concerned about uncertainty, we're very fundamentally care about estimating the uncertainty of our estimates here and getting good predictive inferences that are well calibrated. So we typically do a lot of things like posterior predictive checks that aren't exactly like, say, computing Bayes factors or doing model selection like that.
Is it possible to add some of our models to the pool of the models that you have?
Well, you basically write whatever model you want in this. It's a programming language that basically lets you declare a model like this and write any kind of model you want. Down at the C++ level, you can start adding your own functions. So like people have added things like Wiener diffusion processes and things, and we're building in a lot of pharmacometric models because we're working with drug trials. So we're building in special stuff for that. So you can make it more efficient by building it in at the low level.
Is there a plan to develop a parallel version of SCAN?
Well, it runs in parallel now, at least among multiple chains. So we can do the embarrassingly parallel thing of running 4 chains at once. Most of our users are in a setting where they're using this thing on a notebook computer. They don't really have more than 4 cores to go after. The next thing we're looking at in terms of parallelization is all of our matrix stuff is sitting on top of a C++ matrix library called Eigen, which is really great. And they're opening up some various kinds of low-level parallelization, both GPU parallelization and CPU parallelization that we should be able to exploit under our models. But in general, the fact that we compute derivatives for all of our densities makes it very hard because the derivative calculation with the way the chain rule works has a bunch of ordering constraints on it that we'd have to solve in general if we wanted to do like real massive parallelism. We're also working, like Andrew Gelman's also working with some people on some models, some real parallel models where we can go out and do data parallelism and then combine the things, various forms of expectation propagation and max marginal likelihood where we'll be able to, and we also have streaming examples for variational inference where you can stream the data in. That's not in our public interface, it's just in some branches that ALP and other people used for papers. So. Sorry, I don't want to hog this. I should probably get out of the way now.